Mathematicians use mathematical induction to prove a statement involving a positive integer n. Sometimes we combine mathematical induction and a pattern recognition to write a formula for nth term of a sequence. Sometimes we use it for finding the sum of a power of integers, or we can find a finite differences of sequences. In these examples, we can see that the first sum of the sequence, we call that S1. S1 is equal to 1 is equal to 1 squared. Now notice these sequence that we're only adding the odd numbers together. So S2 will be adding the first two odd numbers together, and that's going to be 1 and 3, which is equal to 2 squared, or 4. S3 is equal to 1 plus 3 plus 5, which is equal to 9, and that's going to be 3 squared. We continue on this pattern. We can see that every time we add several odd numbers consecutively, we end up with how many numbers we're adding, starting from the first number, and that's going to be squared. So S5 would be 5 squared, S6 will be 6 squared, S7 will be 7 squared. So from the pattern we figured out for the first 6 numbers, we notice that the sum of the odd numbers will give me the square of the numbers, how many I'm adding together. So Sn would be n squared. So S20 would be 20 squared. Notice that 2n minus 1, this is the an terms of the sequence for odd numbers. So when n equal to 1, so we can say a1 equal 2 times 1 minus 1, that's going to give me 1, which refers back to the first term of the sequence. So when n equal 2, we can say, a2 equal 2 times 2 minus 1, that's equal to 3, which is the second term of the sequence, and so on. So if I want to figure out what ak is, all I need to do is replace the k by n, replace the n by k, and that will give me 2k minus 1. The fact is, doesn't mean that because we found 6 number consecutively that works for that formula, this formula is true. For example, one of the famous formulas is fn equal 2 to the power 2 to the power n plus 1. This is supposed to be to give me the prime numbers for any value of n. So the answer over here for substituting n value will be a prime number. Notice when n is equal to 0, so then 2 to the power 2 to the power 2 to the power 2 to the power 0 plus 1 equal 2 to the power 1 plus 1 equal 3. So that is a prime number. When I put n equal 1 again, so it's going to be 2 to the power 2 to the power 1 plus 1, which is equal to 2 to the power 2 plus 1, which is equal to 5. That's also a prime number. It works also for 3. When n equals 3, we get f3 is equal to 257, which is also a prime number. If we go to f4, we get 65,537. Even though the formula worked for the first 4 numbers, when it comes down to the fifth number, you can see that substituting n equal 5, we end up with this huge number over here. And this huge number is the product of these two numbers, and therefore when n equal 5, that formula didn't work anymore. So which prove that this formula is not good for all n. It's only good for 0, for n equals 0, 1, 2, 3, and 4. Maybe for some other n's as well. But at least we found one number n that this formula doesn't work for it, and that number is 5. So we have seen just already that it doesn't matter if a pattern works for several values of n, does not mean that this is a formula or it is going to work for all n values. In order to decide and make a decision that a particular pattern is a formula or is a rule, we have to use one of the legitimate proofs in mathematics to show that it will work for all n, regardless what the value of n is. One of those proofs is called mathematical induction. The principle of mathematical induction is we let Pn, P suppose n, to be the statement involving the positive integer. Another way, we just wrote it down on the beginning of this previous slide that it was Sn. So we can use a Pn over here, it's okay. First, we need to show that the first value comes out from the formula correctly. Another way, remember about the formulas with the adding the odd numbers. We showed that the first number, that was 1, or P1 in this case, would equal to 1, which is equal to 1 squared. So this is true for adding all the odd integers. Then we want to assume that this formula is true for all values up to some value we're going to call k. For example, we can say this is true for p of k. So p of k would equal to k squared. So that's basically our first. We have to prove this statement, it's true. Then the next step we say, okay, let's assume this is true for all values up to k. So now for the mathematical induction, we have shown that we say P1 is true, and then we assume pk is also true. Our next step is we need to prove pk plus 1 is also true from the two assumptions we make from those particular numbers. And with that, if we can prove this at the end, then we can say this is a formula, or this is a rule that we have to use for all math. So it becomes a formula. It is important when we're dealing with mathematical induction to go ahead and determine all the values that we really need. At the beginning, we talked about the sum of the series of odd numbers, which is 1 plus 3 plus 5 plus 2n minus 1, and that should give me n squared. So in this particular summation we have S1 is nothing more than the first term of the series. So that's going to be 1. And then S2 is 1 plus 3, and that's going to give me 4. So notice we're looking at the first two numbers of the series. This is for the second sum. For the third sum, we're looking at 1 plus 3 plus 5, and that's going to give me 9. So this is the third sum of the series. However, we are interested in Sk. Then Sk, what is that equal to? We're going to add all the numbers from 1 up to Sk, up to Ak. So that's going to be 1 plus 3 plus 5 plus 7 plus, I'm going to put a 3 dot to indicate that's going to be ending where? At Sk. Now notice, to figure the Ak term, we're going to use, instead of n, we're going to take it away and replace it by k. So that's going to be 2k minus 1. And this should give me k squared. Now, to figure out what Sk plus 1 is, again, we're going to add all the number up to k plus 1. So that's going to be 1 plus 3 plus 5 plus 7 plus all the numbers plus 2k minus 1. This is up to k. Now if I want to add the next term, that's by replacing n by k plus 1. So it's going to be 2 times k plus 1 minus 1. So this particular number over here would be your AK plus 1 that we are looking at. So every time I want to add the next term, all I have to do is add the next element of the sequence given. So now let's go ahead and use mathematical induction to see if we can prove the sum of all odd integers will give me n squared, as it says. To start with this, so first we're going to have to prove that S1, or the first sum, is really works for that formula. Now notice, the first sum is the first number in here, which is 1. And if I use the formula over here, that's going to be 1 squared, and those two are equal to each other. So in this case, we showed that the first sum follows the formula. So now, for the next step, we're going to go ahead and make the assumption that this formula is also true for Sk. And of course, if this is true for Sk, then I'm going to take all the numbers on the left-hand side up to n equal k. To find those numbers, you just replace the left side by the numbers given, and instead of n, we're going to replace it by k, and then this is going to give me k squared. So now the next step, we have to show that Sk plus 1 is going to equal to k plus 1 squared. Now, for the third part, we need to prove the fact that S of k is going to equal to S of k plus 1 is going to equal to k plus 1 squared. So we do have a whole lot of ways to work with this. So let's go ahead and work with what they have. According to what we said before, then S of k plus 1 will be all the number up to k plus 1. So notice it's going to be 1, 3, 5, 7 up to this number plus the next term. This is the next term when k equal k plus 1. And we go ahead and separate those two a little bit on these two. So those are the first step. This is your S of k, and this is the next term, ak plus 1. So if I look at these, but then we already know that S of k, from the previous assumption, we said it's equal to k squared. And then if I simplify this, so you end up with a 2k, and of course 2 minus 1 would give me 1. But this is nothing more than k plus 1 squared. So we're looking for two numbers. Their product is 1, and their sum is 2. And those two numbers are k plus 1 times k plus 1, which is k plus 1 squared. And therefore, we proved that this is equal to that, and this is basically what we need to show in order to tell that n is true for all of this, for all values. Or this equation is true for all values of n. So this is our conclusion written on the bottom of the screen. Okay, in these particular examples, we're looking at two things. First, we need to find a formula for this particular sum given, and then prove by induction that this formula works for all values of n. So how do I find the formula for this particular summation? First, we're going to look at S1. If you remember correctly, we said S1 is equal to the first term of the given summation. And in this case, it's going to be 1 over 1 times 2, which is 1/2. Now, let's stop at this for a second and then continue on. The second term of the summation is 1, or the second sum actually, will be adding the first two terms. So that's going to be 1 over 1 times 2 plus 1 over 2 times 3, which is 4 over 6, and that's 2 over 3. And of course, on the third one, we're going to add the first three terms, and then we end up with 3 over 4. So this is the first one, this is the second one, and that's the first one. Now, sometimes we can recognize the pattern quickly. For example, for these particular numbers, you can see the top number is 1, 2, and 3. So that tells me the first number or the top number is always going to be whatever the subscript is. So if I'm looking at sk, for example, then I already know that sk is equal some k on top. So because the pattern is continuing on these ones. If you look at the bottom number, and you can see right away that this 2, for example, over here is one more than the top one. This 3 over here is one more than the top one. This 4 over here is one more than the top one. So if the top one is k, the bottom one is going to be one more, and that's going to be k plus 1. So basically, the sum of all these numbers is going to be the following formula. Now all we have to do is use induction to prove that this formula works for this particular pattern given. So now this is the formula that we arrived to from our patterns. So now we have to use induction to prove this formula. We don't have to prove S1 in this case because it's already proven in the previous slide. This is where we got the pattern from. So in this case, all we have to do is assume that this is true for sk and show it will be true for sk plus 1. So now here is what sk plus 1 is. Sk plus 1 is going to be equal to all of this plus the ak plus 1 term. The ak plus 1 term is replacing k over here in this case by k plus 1 and also this k by k plus 1. So notice the first k plus 1 will give me that. And then if I put k plus 1 instead of k over here, so we have k plus 1 plus 1. And that's going to give me the k plus 2 over here. But we already know that all of this together, based on the formula on top, is equal to k over k plus 1 plus the next term that we have over here. So if we find a common denominator for this, so that's going to give me equal to, now notice a common denominator for this would be k plus 1 will be k plus 1 times k plus 2. So this is for the first fraction, plus second fraction should be again k plus 1 times k plus 2. So in the first fraction we already have the k on top times k plus 2 because we already had the k plus 1, now this is 2 again, plus from the second fraction we only had 1, and it's really we didn't change that fraction, so it stays the same. So if I add these up together, it's going to be, we add in the top number, so that's going to be your k times k plus 2 from the first fraction, 1 from the second fraction. We can multiply, expand this term, so this is k times k, that will give me your k square. K times 2 will be the 2k over here, and we have a plus 1 which is right here. So this is basically what this is equal to. And from the previous slide we did have k square plus 2k plus 1 on top. On the bottom we had k plus 1 times k plus 2. If we try to factor the top number, then we're looking at two numbers, we multiply, we get 1, and then when we add them, we get 2, and those two numbers are 1 and 1. So that's going to give me k plus 1 times k plus 1 divided by k plus 1 times k plus 2. And therefore, or you can say it is k plus 1 squared. I'd rather leave it in this fashion on top, simply because now I can see that we have a k plus 1 and a k plus 1. Both of these cancel out, and the final answer is k plus 1 over k plus 2, which is simply your S of k plus 1. So the proof is done, and based on that, now we can say by mathematical induction the hypothesis is valid, or it's true for all n. So let's go ahead and repeat the example you looked at in the previous slides by doing it different ways. To figure out the a's of n terms of this sequence is, first we're going to go ahead and subtract those two terms from each other. Another way, 5 take away 3 is 2. 8 take away 5 is 3. And then 12 take away 8 is 4. 17 take away 12 is 5. And then 23 take away 17 is 6. Since the difference at the beginning was not the same, I'm going to repeat the process one more time by subtracting the consecutive terms of this sequence. So we're going to go 3 minus 2 is 1, 4 minus 3 is 1, 5 minus 4 is 1, and 6 minus 5 is 1. Now since the second difference is 1, then we know this is a quadratic because we had to do it twice. And the a term, or the a coefficient in that quadratic, is half what you got in these numbers. So since the numbers are 1, so half would be 1/2. To figure out what b is, let's go ahead and write the sequence. Now notice, a's of n now, the first term is 1/2 n squared plus whatever I'm going to get on the rest of it, so I don't know yet. So let's figure out what's 1/2 n squared, replacing n by 1, 2, 3, 4, 5, and 6 to see whatever answers we get. So now, if I replace n by 1, so 1/2, 1 squared will be 1/2. 2 squared is 4, divided by 4 is 2, divided by 2 is 2. 3 squared is 9, divided by 2 is 9/2. 4 squared is 16, divided by 2 is 8, and so on. Okay, now we're going to get a new sequence by subtracting the original, the one we started with, which is that one, minus this particular one we got so far. So if I subtract these, now notice 3 take away 1/2, it's going to give me 5/2. And 5 take away 2 is 3, and so on. So this is now the new sequence I'm going to be dealing with for finding B and C. So again, we're going to do the same thing we did before. We're going to subtract each 2 consecutive terms of the sequence. So 3 take away 5/2 will give me 1/2. 7/2 take away 3, so 3 is 6/2, so that's going to give me 1/2 again. And if I continue, I'm going to get 1/2 for every one of those subtraction. So because the subtraction on the first time happened to be all the same, then we can say B is whatever number you get. So that's your 1/2. So now I want to figure out what is, now notice the second term of the sequence is 1/2 n. So now I want to figure out what this sequence is going to be like. So 1/2 n, replacing n by 1, 2, 3, 4, 5, and 6, we get the following. When I put 1 for n, I get 1/2. When I get 2 for n, I get 1, 3, this is for 4, 4, 5, 4, 6. So now we're going to repeat what we did before. But now my new sequence is this one. I'm going to subtract this minus that. So if I subtract those, now notice 5/2 minus 1/2 will be 2. And then 3 minus 1 would be 2 again. 7/2 minus 3/2 will be 4/2, which is 2. And if I continue for 4, 9/2, and 5, subtracting 2, 5, and 3, I'm going to end up with the same number all over. It's going to be 2 all the way. So since this is the third one, so since all of these are the same, then we know C has to be 2. So now with that, my nth term would be an equal the first one we got, which is 1/2 n squared plus we got B is 1/2, so that's going to be 1/2 n plus C, which happened to be 2. And this is another way of finding a quadratic sequence that is given its term.